When looking at the wave nature of electrons, de Broglie, this guy, French guy named de Broglie, he did a whole bunch of crazy math, um, but in the end he got to an equation which is basically equivalent to what we saw from considering the photoelectric effect and the momentum. De Broglie figured out that the wavelength is connected to the momentum something carries. It's an equivalent expression, but he came up with it in a more complicated way. If we know the momentum of something from its particle nature, we can figure out the wavelength that goes with it. Momentum is always mass times speed. So for this one, we know that we're shooting an electron at 1.5 times 10 to the 7 meters per second. We can figure out the associated de Broglie wavelength that goes with that electron. It's literally just a matter of plugging in our values. H is a constant. It's always at 6.626 number. It's crazy small, 10 to the negative 34. The mass of an electron is 9.11 times 10 to the negative 31. And the speed that I made up is this 1.5 number. Now, you may be wondering about special relativity. Can I just use that 9.11 number? Because it's going so crazy fast, isn't it behaving as if it has more mass? The short answer is yes, we should be taking into account special relativity. But if you think back to when we talked about special relativity, gamma stays like 1.000 until we get into the 10 to the 8s. So at a speed of anything times 10 to the 7, we can kind of round off the gamma to 1 and get an okay answer. So it's not that I'm skipping special relativity, it's just that at this speed, special relativity doesn't have an impact to worry about. When I crunch out the math on this, I get a de Broglie wavelength of 4.9 times 10 to the negative 11 in meters. That at first glance is a crazy small number, but compared to the size and the scope, the universe where an electron would sort of interact, that's not crazy small. That's like a normal size. Electrons are crazy, crazy small. That's a crazy, crazy small distance. If we could fabricate a double slit that had a d value in the order of 10 to the negative 11 meters, that's small enough that when electrons pass through it, they could fit through those small openings, and we would see the wave nature of those electrons.